So we're going to start today by asking the question, what is boiling? So I want you to pause, I want you to try to remember, and we'll kind of go from there. So the boiling point of a substance is the point where the vapor pressure equals atmospheric pressure. Okay, so we're talking mostly about volatile compounds here. So I have a little video here that'll serve as a reminder.
A volatile liquid evaporates readily. Consider what happens to the molecules when we put a volatile liquid in this flask. Some molecules leave the surface of the liquid and enter the vapor state. The vapor above the liquid exerts a pressure called vapor pressure in the flask. In contrast, a slightly volatile liquid has a lower evaporation rate, so fewer molecules enter the vapor state above the liquid. Non-volatile liquids have little discernible evaporation, so no vapor forms above the liquid.
Okay, so simple enough, right? Volatile liquids, the molecules aren't held very tightly. They have weak intermolecular forces. So when they have a little bit of energy, they are free to move to the gas phase. And then those gas molecules are going to exert a pressure, which we know about. So what effect do you think adding salt to water, okay, water is a volatile liquid. We know that because you can leave it out and it'll evaporate. So what effect do you think adding salt to water would have on the vapor pressure of water? Well, let's take a look at a picture. Okay. In just pure water, we're going to set up a equilibrium, okay, where vapors are going to be entering the water at the same rate that vapors are going to be leaving, okay? And this is all going to happen at the surface. But if you add a non-volatile solute, so in this case they add sucrose, okay, that surface area is going to contain not just water molecules, it'll also contain sucrose molecules. And those sucrose molecules will also be interacting with the water. So those waters are going to have more interactions and less surface area in which to leave. So that to me should say that the vapor pressure, the number of gas molecules above the surface of the liquid, should decrease, which means that the vapor pressure should decrease. Okay? So I also have another piece of important evidence here. Okay? A 1 molal solution of glucose, C6H12O6, decreases the vapor pressure of water by the same amount as a 1 molal solution of sucrose, C12H22O11. Okay? So that to me says that the identity of the solute doesn't really matter, okay? We decrease the vapor pressure by the same amount, and it's only based on the concentration. Okay, this is an example of a colligative property, a property that does not depend on the identity of the solute, only on the concentration of the solute. Okay, now we said that the vapor pressure is going to decrease. Okay, so if the vapor pressure decreases, you're going to have to increase the temperature in order to get the vapor pressure equal to atmospheric pressure. So I have a little video on that as well.
The boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the prevailing atmospheric pressure. Because the vapor pressure of a solution containing a non-volatile solute is lower than the vapor pressure of the pure solvent, more heat will be required to raise the vapor pressure of the solution
to equal the atmospheric pressure. Therefore, adding a non-volatile solute to a solution raises the boiling point. All pure solvents have a characteristic molal boiling point constant. The boiling point for water, for instance, will increase by 0.51 degrees Celsius for every 1 molal addition of non-volatile non-electrolyte solute.
Okay, so because we've decreased the vapor pressure, that is going to have an effect on the boiling point. So notice that if I move down here, now in order to get back to 1 atmosphere, the boiling point, the atmospheric point, okay, I have to increase the temperature. So there's an increase in the boiling point of the solution, okay? And if I follow this line down, that means that this is it's gonna have the same slope, right, as the pure solvent. The solution should have the same slope, and that means it's gonna meet this transition at a lower point. Okay, so this is freezing point depression now.
A solvent, such as water, freezes when the temperature falls below the solvent's freezing point. When molecules of a non-volatile, non-electrolyte solute separate the solvent molecules, it becomes more difficult for solvent to form a solid network. The network, therefore, does not form until the temperature is below that of the normal freezing point of the pure solvent, resulting in freezing point depression. In general, the more solute you have, the greater the freezing point depression. All pure solvents have...
We'll stop there. Okay, so what I can gather from this is that the change in temperature, let's say of the freezing point, so the freezing point depression is going to be directly proportional to the molality of the solution. Haha. Okay, so how do you go from a proportionality to an equality? Yep, you add a constant. And here is yet another k. Okay, so the freezing point depression, okay, this is freezing point depression, is equal to some constant times the molality of the solution. Okay, this is the molal freezing point constant. Okay, and importantly, this depends on the solvent, because this is really describing the change in temperature of the solvent due to the fact that you've added a solute. Okay? Now, we're going to have a very similar equation for boiling point. Delta TB equals KB, boiling point, yes, molal boiling point constant, times the molality of the solution. Okay, now, in this case, the deltas, well, take a second, think what delta means, okay? Think what delta means. Delta is final minus initial. All right, so in this case, let's say freezing point depression, okay? The final is the freezing point of the solution, and the initial is T pure. This will give us how much of a decrease there is due to freezing point. And notice that this should be negative, right? If, let's say for water, T pure, the freezing point of pure water is 0 degrees Celsius, so the freezing point of a solution should be less than 0. So that's going to be negative, okay? And with boiling point, the boiling point of water is 100, okay? So the delta is going to be positive because the final temperature is going to be higher than 100. Okay, I think it's time to start some problems. Determine the freezing point of a water solution of fructose made by dissolving 58 grams of fructose in 185 grams of water. Okay, now, one of the things that I'm going to tell you here, the compounds that we're going to be doing in this unit are going to be kind of beastly to get molar masses of. Use the Lentech molar mass calculator to help you out. All right? So, determine the freezing point of a solution of fructose. Okay, so delta TF equals KF times the molality. Now, this gives me freezing point depression. Okay? And there are kind of two ways that I can go about this. All right? The first one way to do it is I can calculate the freezing point depression, and then in another step, figure out the actual freezing point. Okay? Or I can do it now. And especially for freezing points of water, doing it at the beginning is actually a little easier. Okay? And the reason for that is that delta TF, as I know, is T solution minus T pure. Okay, and I know that the freezing point of pure water, okay, because that's my solvent, pure water has a freezing point of 0 degrees Celsius. So delta TF equals T solution. Okay, so I'm going to show this. All right, this goes away. So T solution equals KF times M. Now, one of the most common mistakes that I see made is being unclear whether you're finding freezing point depression, okay, delta T, F, or an actual freezing point, which would be T solution, okay? You have to pay close attention to this. All right. Now, the next thing that I need to do here is I need to get the KF, all right, and the M. Now, KF is a constant, all right? So if you go to the master document for this unit, drive, master document, I have put the table from the book in here. Okay, so here's water. I have molal freezing point, okay, or sorry, normal freezing point in degrees Celsius, and I have molal freezing point constant, okay? So molal freezing point constant for water is negative 1.86 degrees Celsius per molal. So KF is negative 1.86 degrees Celsius per molal. Now, what about the molality? Well, I don't have the molality, okay? I'm given a mass of the solute and a mass of the solvent. So I need to find the molality, okay? And remember that molality is moles solute over kilograms solvent. So what I want is I want moles of fructose over kilograms solvent. So all I have to do is start out with my 58.0 grams of fructose over my 185 grams of water. Okay, now I need to take my grams of fructose to moles of fructose. Okay, So I use the Lentech molar mass calculator, and I get 180.15 grams fructose and 1 mole fructose. Okay, so there goes my grams of fructose. And now I need to get my grams of water into kilograms of water. So 10 to the third grams water and 1 kilogram water. Grams of water. And now my units are moles of fructose over kilograms solvent water, which is the same thing as molality. So that means that this cancels with this and this. And the unit I'm left with is degrees Celsius, which is what I want. Okay, now I can plug this into the calculator. And it's important that you do this in the correct order. Okay, I do it kind of stepwise. And what I get is negative 3.24 degrees Celsius. Okay, so that's your first problem. Now this one is pretty difficult. Okay, most of the other ones, this is a long problem. Okay, so some of the other ones will be a little bit shorter.